Going live. You're live. All right, I'm playing the video. You start.
Good morning, everyone. I hope you enjoyed yesterday's sessions. Picking up from where we left off, today we have with us Dr. Shrikant Vemula for the first session. He is going to enlighten us on topics like catalyst synthesis and industrial example of catalysis. Dr. Shrikant Vemula has completed his PhD in chemistry from Institute of Chemical Technology. Currently, he is associated with Hindustan Platinum Private Limited, which is a catalyst manufacturing organization. His other areas of research expertise is in wet air oxidation. He has published and presented his research work in various international journals and conferences. Without taking much time, I invite Dr. Shrikant for the presentation.
Good morning, everyone. Thank you for the kind introduction. I'm Dr. Shrikant Vemula. I'm currently working with Hindustan Platinum Private Limited. It's a catalyst company itself. We synthesize mostly heterogeneous catalysis. I'm presenting my work, the webinar on catalyst. So we'll talk about what is a catalyst, the type of catalyst, application for its sustainability. The topic is sustainable, so we will link up how they are produced in the industry, some characterization of the catalyst, and followed by the question and answers. Okay, what is a catalyst? A term called catalyst is derived from Greek, which means to untie or to pick up a substance that causes or accelerate the chemical reaction without itself being affected. The reaction brought about by catalyst is called as catalysis. It was invented by a chemist named Elizabeth Fulham in 1794 while working on novel work in oxidation reduction experiments. Later, Berzelius in 1835 gave the term catalysis to describe the reactions with catalyst. When we use catalyst, the reaction is called as catalysis because we are using catalyst and we are amplifying some parameters. So that process is called as catalysis. Now we will talk about what is energy of activation. So the reactant requires some amount of energy to produce a product, form into product. They utilize some minimum amount of energy, and this energy is called as its activation energy, EA. So you can see this graph. There are green lines and the red path. So green path indicates, it shows when the catalyst is used, the activation energy is little lower. When the catalyst is used without catalyst, the activation energy required is more. But the red path indicates that. Catalyst is a substance which can lower this activation energy and hence gives a sustainable solution. Here again you can see energy required for transferring the reactant into product is less when the catalyst is used, and without catalyst the energy required is more. Catalyst reduces the activation energy by providing an alternate pathway for the reaction to occur. catalyst allows the reaction to be carried out with a lower energy consumption. We have some advantages of using the catalyst. We will get a better productivity, and it is also economically very feasible to use catalyst. It has a simpler reaction step with a low investment cost, milder reaction condition, that we don't want any harsh reaction. We can we can carry out the reaction at lower temperature and lower pressure also. Moreover, we can control the reaction process, and also we can reduce the generation of any waste which is occurring during the reaction. So we can make the complete reactant transfer into the product, so there will be a lesser generation of any waste or the byproduct, what you can say. We have basically two types of catalysis, that we have homogeneous catalyst and heterogeneous catalyst. So homogeneous catalyst is a catalyst where the reactant and the product with the catalyst all are in the same phase. It can be a liquid or can be in a gaseous phase rather. Also, and the next one is a heterogeneous catalysis, where there is a difference in the phase between the product and the reactant and the products. Catalyst and the reactant and the product. We'll talk about in brief about what is homogeneous catalysis. Homogeneous catalysis, as I told you, that the phase remains the same. Both the phases are same. The catalyst and the reactant and the product. The phase remains the same. It is in soluble phase if it is in liquid. So, catalyst forms an intermediate compound with one of the reactant. If we have two reactants, one of the reactant will form an intermediate with one of the reactant. This intermediate later decomposed to form a catalyst. So you can see the reaction. It is multiple step reaction, rather more than one step reaction. When you see a reactant A reacts with reactant B, what happens is reactant A react with the homogeneous catalyst in one. It forms an intermediate catalyst, rather intermediate product. This intermediate product again reacts with reactant B and forms product, and catalyst is set free. But then in homogeneous catalysis, the product and the catalyst both are in the same phase, so it is in the mixer form, since it is a soluble one. Mostly we use transition metal ions as a homogeneous catalyst. There are many pros and cons for using homogeneous catalysis. Well, pros is it is highly selective because it is soluble in the medium and its active sites are available for the reaction. Hence, it is easy for the reactant to access the catalyst. Whereas, at the same time, we have some cons. So, as I told you that after the product is formed, the product and the catalyst both are in the same phase. So, it is very difficult to remove, rather separate them, and hence the process becomes very complicated. More than that, like the catalyst, the reactor in which the reaction is carried out, it also gets corroded over the time, and also it generates the waste, and it is only stable at milder temperature. At higher temperature, it does not work. Rather, it can decompose, or it has a limitations of working at the higher temperature. So we will talk about now about the heterogeneous catalysis. We have many advantages of using heterogeneous catalysis. So heterogeneous catalysis has an active site on which the reaction takes place. We will talk about it in the next slides. Mostly metals are impregnated on the solid support. The solid catalyst which supports which we can use can be an activated carbon, can be a silica, alumina, zeolite, TiO2, titana, or calcium carbonate, or etc. So very advantages of this is it is easily separable, and we can use it many times, multiple times we can use it. We can separate, wash, and again we can reuse for the next reaction. So here some basic general heterogeneous catalysis, the mechanism of it. So what happens first on the catalyst surface, reactant get adsorbed. So this process is called adsorption. Initially, both the reactant get adsorbed on the reaction, the catalyst surface, and the reaction takes place. It forms a product. Once a product is formed, it gets absorbed, and then we can isolate the products, and the catalyst is set free. Some more types of catalysis, like we have. The name says positive catalysis is definitely increases the rate of reaction. by lowering the activation energy, and hence we will get a higher yield. So, for example, in Haber's process of preparing ammonia, we use iron as a catalyst, as a positive catalyst. Same way, we have a negative catalyst. The name suggests that it decreases the rate of reaction, increases the activation energy, and thereby the yield also decreases. For example, for decomposition of hydrogen peroxide into water and oxygen, the rate is retarded by using an acetanilide, because we want sodium hydroxide to be intact. Sorry, sodium peroxide to be intact. We don't want that to be converted into water and oxygen. So we use acetanilide to reduce this activity. That's why this is an example of negative catalysis. As some terminology, that is, we have promoters and poisons. Promoters are also called as accelerators, which increases the activity of catalyst. Example, we have in Haber's process, we use molybdenum or mixture of potassium and aluminum oxide, which act as a promoter, which amplifies the activity of the catalyst. Same way, we have catalyst poisons or inhibitors. Definitely, the poisons itself, inhibitor, the term itself says that it will decrease the activity of catalyst. So, where it is used is in the hydrogenation of alkynes to alkenes. So, when the catalyst palladium is poisoned with barium sulfate in quinoline solution, and the reaction is stopped at alkenes level, so that it will not go further to alkanes. We want alkenes only, so it will be stopped at that step only. Such catalyst, this catalyst is called as Lindlar's catalyst. Then, mostly catalyst is definitely a sustainable solution. Why? Because it gives a favorable condition, safer condition for everyone to use it. Rather, all the chemists to use it. It can, I mean, the reaction takes place at a lower temperature, pressure. It will utilize lesser fuel, and hence the pollution also created will be less. Process is very quick. It saves times and also the money. It gives high productivity, and the product has high purity. Hence, thereby we have a greener chemical solutions. So that's what we say. The solution for tomorrow, using today's technology. Sorry, solution for tomorrow using today's technology. So here is one of the example. Using preparation of ammonia by using Haber's process. So we have hydrogen and nitrogen. It is pumped in the ratio of 1:3 by volume in a reactor containing iron as a catalyst. The reactants are subjected to a heating temperature of 450 degrees centigrade with 200 atmosphere pressure. At this, the reaction between hydrogen and nitrogen takes place, and we get a liquid ammonia. But before getting liquid ammonia, it is passed to a cooling chamber where this gaseous ammonia is converted into liquid ammonia. The unreacted gases are recycled back to form with the reactant to form again liquid ammonia. Another industrial examples, we have hydrogenation of ethene into ethane on the surface of nickel. So what happens first, on the catalyst surface, hydrogen get adsorbed, and later ethylene comes, it adsorbs, forms a reaction, and then it forms ethane. After the reaction is formed, the ethane get dissolved from the catalyst surface. Then we have more applications for the catalyst. Actually, almost nearly 85% of the chemical industry use catalysis for their process. Either any unit process, they use at least for one process, catalysis is required. We have pharmaceuticals industries using catalyst. We have fine chemicals industries, petroleum, fertilizer. Every industry mostly use catalyst. Catalyst is also used for the pollution control. For example, for the toxic gases, the harmful gases are converted into harmless ones by using the catalyst. There's adsorption of the harmful material on the catalyst, and it is like a filter. It can act as a filter also. Then for liquid also, for deodorization and decolorization of any liquid, we can use catalyst. So most of the industry prefers the solid catalyst, that is heterogeneous catalysis. Since I said that it is easy to separate, so most of the industry prefers heterogeneous catalysis. Then this is a basic structure, how the process starts and how the process ends, how they are designed, how the catalysts are developed. A small introduction for that. So initially for every work, what we do the research. So here also, first the research is done. The research consists of the literature, the screening of the catalyst, that which catalyst would be applicable for which reaction and all that. Then the catalyst is characterized, chemical reaction, I mean the kinetics of the reaction is studied. Then the process is developed. For development, the catalyst life test on the bench scale is done. The designing of pilot reactor is done. Then the catalyst geometry is considered, that what kind of geometries to be taken, like it should be taken in the extruded, it should be taken in the powdered form, how they are taken, that has to be studied. Then the process modeling and the economic analysis is done. The pilot plant test is done, consisting of the catalyst redesigning, the process model development is there, and of course the economic analysis is definitely a very important parameters, because definitely everything we are doing it for the economic also only. So economic analysis is definitely to be done. Next, once this everything is done, then we can talk about, rather we can make a plant demonstration, that erection of the demonstration plant. Catalyst life is retested. You have to check with on the plant that the catalyst cycle is, I mean the life, how whether it is getting centered, deactivated, or likewise. Then the plant is constructed. With the compactable materials, it has to be constructed. Otherwise, the corrosion or any other things can happen. So the pressure test also has to be done. And then once all these parameters are checked, then we can start with the operation of the any plant. So the basic criteria for the good catalyst is initially the activity. So the activity of the catalyst is its ability to increase the rate of particular reaction. I mean, how many times the catalyst can be reused is the activity. For example, if we are using catalyst for one time and then for the second time we are unable to use because maybe of deactivation or sintering or something like that, then the activity is very less and then it is unfeasible for us to use the catalyst. So that process, that parameter has to be checked. That is feasibility for the multiple cycles, that one catalyst can be reused many times. So higher the number of the cycle, higher is the activity of that catalyst. We also term it as turnover number. So that the number of times that catalyst goes through the cycle to convert the reaction into the product is called its turnover number. Second, criteria for being a good catalyst is the selectivity. The ability of the catalyst to direct a reaction to yield a particular product is referred to as a selectivity of the catalyst. I means we are taking the reactant and we want a product. So how much yield we are getting of the product is the selectivity of the catalyst. Most of the catalysts have the highest selectivity, high specific. Most of the catalyst has selectivity towards a particular product. For example, the reaction with same reactant but different catalyst may yield different products. So that happens. That's why we have to screen the catalyst before we use it. And definitely a stability of the good catalyst. I mean, the criteria for the good catalyst is also a stability. So the stability is defined as the ability to resist the deactivation. The catalyst should not deactivate. If it is deactivating in the initial cycles, then the stability is less. But if it is giving many turnover, rather much cycles, then we say that the stability is very good. So more stable the catalyst, greater is the turnover number and greater is the product. So the stability also indicates it should resist the iteration due to the mechanical movements or the pressure shock during the vortexing. I mean, during the stirring of the reaction, it should not iterate. It should not break, especially when we are using the extrudes or the pallets, the catalyst pallets. So one of the method of preparing catalyst is precipitation method. It's very simpler method. So I'll just explain you how it is done in general. So the metal solutions are taken and the precipitating agent is also taken. The precipitating agent can be NaOH or sodium carbonate, which increases the pH. At the increased in the pH, what happens? A metal solution precipitate into hydroxide. Once this precipitation is done, then we will keep it for aging so that all the precipitation settles down. Once the aging is done, then we will wash it by using decantation. And then we will filter it. And the filtrate is washed. Once it is washed, we will wash it to remove all the sodium or chloride content in it. Once it is done, then we will dry it, we will calcine it, and then that is the catalyst is shaped into a desired size, and then it is activated. Next process is impregnation. So this is mostly versatile, or many of the industries are using this impregnated catalyst. So in this, the support and the metal precursor are, rather, the metal precursor is impregnated on the support. So there are two kinds how they are done. So we have dry impregnation and we have wet impregnation. So in the dry impregnation, it is also called as incipient wetness. Here, what happens? The support has some volume of pores. That number of pores is equal. The equal amount of solvent is used so that all the pores will be occupied by the solvent, or rather, it can be a water, a metal solution. All the pores will be occupied by the metal. Next is wet impregnation. So in the wet impregnation, what happens is the pore size is definitely called calculated, and we take the solvent which is in excess of pore size. So that's why it is called as wet impregnation. I mean, more amount of liquid is there and less amount of pore is there. So there is an excess amount of solvent. Once this impregnation is done, we will dry the catalyst. Once it is dried, then we will go for a thermal treatment. That is calcination, reduction, and activation of that catalyst. You can see this. The support and the precursor are mixed together. Rather, we adsorb. Whether we impregnate on the support, we will adjust the temperature, pressure, and the pH of the process to get a catalyst, a proper catalyst. Here is another one example, that is preparation of ruthenium on TiO2 by using wetness impregnation. So what we do is, the finely divided TiO2 is added to a ruthenium chloride solution, a precursor. It is stirred for 1 hour. After stirring for 1 hour, NaOH is added so that the ruthenium chloride is converted into ruthenium hydroxide precipitation. Once this precipitation is done, then the process is mixed for 1 hour, stirred for 1 hour, and then heated at 333 Kelvin. Then it is allowed to settle. Once it is settled, the supernatant solutions are discarded, washed with the fresh water, and again it is allowed to settle. Once this process is done, then we will reduce the ruthenium by using formaldehyde and NaOH. Once the reduction is done, then we will filter it, wash it, and then it is dried, calcined, and then we get a ruthenium TiO2 as a final product. So there are many processes of analyzing or characterizing the catalyst. We have SEM or FESCM, that is scanning electron microscope. It gives us the surface morphology of the catalyst. Then we have TEM. Then we have FTIR. TEM is used to understand the bulk morphology, the bulk composition of the catalyst. Then we have FTIR. It is used for finding any functional groups on the catalyst. XRD is also used for finding catalyst. BET is also used for the surface, the pore size and related parameters. Hydrogen chemisoption is used for finding the dispersion of the catalyst. The dispersion is the number of active metal, active metal available for the reaction. Then we use TGA to study thermogravimetric analysis. Likewise, we have more like for surface area, pore size, we use BET. Elemental composition of the catalyst can be found out by using atomic absorption spectroscopy. As I said, morphology by using scanning electron microscope, dispersion by using chemisorption, and surface and the bulk composition can be ascertained by using X-ray photoelectron spectroscopy. Thank you very much for listening me.
Thank you, Dr. Shrikant Vemula, for the outstanding presentation. We are very happy to have you with us. Dr. Shrikant has covered the catalyst overview in depth. He discussed types of catalyst, application of catalyst for sustainable operations, industrial production of catalyst, and catalyst characterization in very simple and clear language. Participants, please note the feedback form will be posted in the chat section of YouTube at the end of the session. Now it is a time for question and answer session. Participants are requested to type their questions in chat box for Dr. Shrikant. Over to Dr. Shrikant.
Thank you very much for listening me.
So can we ask you some of our questions?
Yes.
So the first question is, how is the activity and the particle size of a catalyst interrelated?
Yes. So actually, particle size plays a very crucial part in the catalysis. The smaller the particle size, higher is the activity. It's inversely proportional. So if you are taking smaller particle size, the surface area available for the reaction is more, and hence we will get higher activity.
Thank you, sir. So over here, we have a question from Dr. H.K. Sharma. His question is,
Yes.
kindly explain about the isolation of nanocatalysts after catalysis of reusing in further.
Isolation of nanocatalyst.
Yes, sir.
Well,
After catalysis,
heterogeneous catalysis, you're saying?
yes, sir.
Yeah. So that can be separated using centrifuge, or like, I don't know, I mean, depends on the particle size, but nanoparticles have lesser size that can be separated using centrifuge method also. Hello?
Thank you, sir. Yes, sir.
Yeah.
Yes, sir. The third question that we have over here is, while preparing heterogeneous catalyst, which solvent is used?
Mostly water is used because metal solution are mostly used in metal solution. For metal solution, we use water only because you cannot use any solvent. Because it can catch fire if you use any other solvent when it is metal is used. So mostly water is preferred. Mostly water is used.
Thank you, sir, for clearing that up. Now,
Yeah. Thank you.
why do you think is formaldehyde used while preparing ruthenium TiO2?
Yeah. So the formaldehyde is used to reduce the catalyst. For example, the catalyst, the metal solution, metal is in the oxidized state. So we want that to be reduced in the ground state, and that's why we use formaldehyde. So we reduce the catalyst. So that's why formaldehyde is used.
Oh, thank you, sir. So,
Yeah.
what are the important parameters in catalyst selection for any process?
Yeah, that's what I told you. It should have a high activity, selectivity, the particle size depends, and the stable. It should be stable. It should be available for multiple cycles also, so that we can reuse, and the economic cost can also be reduced.
Thank you, sir, for clearing that up. So, do you think that we need to modify the equipment design parameters if one decides to change the catalyst for any existing process?
Catalyst size, you're saying? Change the catalyst size? See, for example, if you can use
fixed bed also, we can use slurry reactor also. Depends on the reactor, depends on the catalyst. We have to check what is feasible, and accordingly only we can carry out the reaction. For the fixed bed, we can use pellets, extrudes also. For slurry reaction, we can use the finer one, powdered catalyst, so we can use.
So the last question that we have is, what do you think are the
Hmm.
appropriate ways to dispose spent catalysts in any industry?
See, dispose is not, because we cannot dispose, we can recycle, because of precious metal. For example, if you're making precious metal catalysts are so precious that we cannot dispose it. We have to recycle it. We can incinerate, we can remove all the support, incinerate, and the support can be burned off, and then we can get a metal solution. And there is a process of recovery also. So we can recover the metal, we can put it back for another catalyst manufacturing also. I mean, we can reuse that metal also. So once the metal is there, it is not wasted. We will use it, even if it is deactivated. We can rather incinerate, rather remove it out, separate the metal and the support, and that metal can be again reused, can be again reactivated.
Thanks a lot, sir. So we have a last
Yeah,
question from
thank you.
Dr. H.K. Sharma again.
Yeah,
His question goes as follows.
yeah,
After centrifugation, how can we separate the
yeah.
nanocatalysts and products of reaction?
Okay, so like if the product is in liquid, or rather like if it is a liquid with heterogeneous, if it is in a different phase, na? Nanoparticles if it is in a solid, and then we have this one, uh, the product in the liquid, then we can separate it by using filtration or likewise. But filtration also, the sieve should be such that it should I mean it should hold that catalyst particle above.
So we have a last question from Jitendra Malusade. How does the dry and
Hmm.
wet etching of a catalyst done?
Dry and wet catalyst aging is done. See,
Etching,
aging is that if we will keep aging, right? So etching or aging,
etching, etching.
etching. Actually, over the time, that is same as the deactivation of the catalyst. So over the time, after the reaction is taken for multiple cycles, it there is a possibility of sintering, deactivation, or any carbon particle of the product get deposited on the pores. So that get etched, or rather, it get deactivated. So that is a thing which happens, and that is what we call as stability of the reaction. I mean the catalyst. If it can resist more etching or more deactivation, then we say that it has a higher stability. Otherwise, we say that the stability is very less.
Thank you, sir, for answering our questions. And I'm sure that the doubts of the various viewers have been cleared up regarding the catalyst. Thanks a lot, sir.
Thank you very much.
Hi everybody, this is Lekha Nirmal. I am a BE Chemical from Thadomal Shahani Engineering College, and then I went on to pursue my entrepreneurial studies from IIM Bangalore. I now co-run an engineering consultancy by the name of PMEC Consultant Private Limited here in Mumbai, India. We provide engineering and design services to customers all across the globe. Well, I'm glad that I chose chemical engineering as a career option back when I was in 10th, 11th, and 12th, and I had to make a choice. Obviously, I did a lot of research and I spoke to a lot of industry experts. And one thing I've realized, even after being in the industry now for quite a few years, is that chemical engineering as a career option is something that opens a lot of avenues for you, in the sense that you can get into renewables, you can get into sustainability, you can get into energy, you can get into research and development, you can do plant design, you can do equipment design, you can get into so many things, you can become an entrepreneur. There are so many things that open up for you, especially now with the whole the whole trend getting into IT and tech, and with COVID happening at the same time, it's a huge realization that efficient utilization and management of energy especially is one major concern and should be definitely addressed too. Talking about this, I am glad that the topic for this webinar is sustainability, because I'm sure that it's need of the hour, and a discussion about this should happen. Looking at the panel, I'm sure that y'all are going to get lots and lots of insights, and it's going to add a lot of value to you all attending the webinar today. One thing I want to tell you all before I leave is that chemical engineers are game changers. Always remember that. All the very best. Thank you.
Good day, everyone. My name is Shulmit Bapat, and I am an alumni of Thadomal Shahani Engineering College. I graduated from Chemical Engineering Department in the year 2008. I started my college in 2004 as well. The only reason I picked chemical engineering was my liking towards chemistry, and I thought it would be a great idea to take up chemical engineering, which was a really offbeat branch at that time because everyone was moving towards IT and electronics and telecommunication, and the IT boom was practically going on. Everyone wanted to move outside of India. But I made this choice. I stuck to chemical engineering. I started in 2004 in a completely unknown environment, thinking, it's all about chemistry, and we'll understand everything from there. However, once I got into chemical engineering, I realized chemistry is a part of it, and there are a lot more things associated with it. Of course, the practical knowledge which comes along with the theoretical knowledge is equally important. Our professors, starting from the second year onwards, because the first year was common, second year onwards, gave us a preview of how chemical engineering is going to look like. There was a very good understanding because the faculty and the students were very intimate with each other. We could approach them, we could ask them questions, we could understand the nitty gritties of chemical engineering. All our professors, to name a few, Sadhna Purohit ma'am, Usha Nambiar ma'am, Anita Mehta ma'am, Thomas ma'am, all of them were always available to help during any questions that we had during our study times. I remember in 2015 we conceptualized an idea. A couple of us together came together and thought, okay, let's come up with a chemical engineering festival, and that's how the birth of Chemorgens happened, which I'm sure still goes on year on year. Probably this year due to COVID, it might not have happened, but it was an idea which kind of conceptualized. A lot of support was given by all our faculty. All the lab assistants were equally involved in the whole process. We had very great sponsors. It brought TSEC into the limelight, at a state level platform as well as at a national level platform where we had universities, students coming from all over India. Um, this gave us a kind of a home like feeling because we were involved in our regular day activities about the chemical engineering department. We had a very good balance between learning as well as practical as well as extracurricular activities at the same time. It was a very good experience, and that's where during this course I decided to kind of stick around towards chemical engineering as well, and I started working with SNC Lavalin post my graduation. I worked with them as a project engineer in Mumbai. Post which I went to United States to do my MBA, and now today, as of today, I'm working with Uralchem, a Russian chemical fertilizer. I handle their international sales for all the chemical fertilizers that they produce. I'm based out of Riga, Latvia, and I can tell you the journey has been totally memorable. It has been an excellent experience. There has been a lot of learnings in the process. We've kept in touch with all our professors. Um, the most important thing was the balance between the practical and the theoretical knowledge. It was an immensely memorable experience as well, and I'm sure all of you today have been gathered for an online webinar on sustainability, which becomes a very integral part of our entire structure today, and everyone's talking around the world about it, and we as chemical engineers have our rightful part to play in all of this. Some of my friends are already working in zero waste management, which also forms a part of sustainability, and it becomes extremely important because if you look at the world around you, there is chemical engineering everywhere, and you will notice the outputs, the products, the raw materials, all associated with some kind of an engineering which has come out of a chemical process. So I'm sure you're going to have a very interesting webinar rather, going forward on the sustainability aspect. And these are my two bits about the whole experience that I've had. And it has been a memorable one, and I hope you all have a very good time during the webinar. And thank you very much, and hope to stay connected. And if you want to know more about my life, feel free to connect with me on LinkedIn, and we could talk more about chemical engineering and the commercial aspect of it as well. Take care and have a good day.
It is my pleasure to introduce speaker for our next session, Mr. Miliend Sawai. He has pursued chemical engineering from Lakshminarayan Institute of Chemical Technology in 1993, followed by Diploma in Business Administration from Mumbai University. After working over 2 decades for various Fortune 500 companies, including Lubrizol India and BASF India in various capacities, he has formed his own company, that is Magnus Confra Solutions LLP, dealing with specialty chemicals business based out of Navi Mumbai. He is also a digital coach and YouTuber. His hobbies comprise of singing, travel and adventure sports and blogging. He also is a secretary of Rotary Club Navi Mumbai and chairman of IFRM, that is International Fellowship of Rotarian Musician Navi Mumbai. We welcome you, sir.
Very good morning and a warm welcome to all who have joined and participating in this webinar today. I thank Department of Chemical Engineering and dignitaries at Thadomal Shahani Engineering College, Mumbai, for giving me an opportunity to connect with you all through this webinar. Well, my name is Miliend Sawai. I am a chemical engineer and alumni of Lakshminarayan Institute of Technology, Nagpur. After over 2 decades of professional experience, having worked with global multinational companies in various capacities, I started my own company, Magnus Confra Solutions Limited, based in Navi Mumbai, and we deal into specialty chemicals. As the world is going digital, so I too have a YouTube channel, the name of Digital Miliend, to connect to the world in the lives of people and community. My today's topic of webinar is chemical engineering and sustainable development, which is very crucial in the current scenario wherein natural resources are depleting faster, challenges like population explosion, global warming, climatic changes, water scarcity, and air and industry pollution, and how chemical engineering pivotal role in sustainable development to make this planet habitable for future generations to come. Well, chemical engineering touches everything from the development of smaller, faster computer chips to innovations in recycling, treating disease, cleaning water, and generating energy. The presentation consists of sustainable development, challenges, and the role of chemical engineering in sustainable development to make the world a better place for generations to come. I have also included brief overview on chemical engineering, job prospects, and opportunities. Sustainable development. Sustainable development is a development that meets the needs of the present generation without compromising the needs of future generations. To achieve sustainability, we must balance social, economic, and environmental factors in harmony. Sustainable development is the pathway to sustainability. So the sustainable development is improving lifestyle, ensure preserving natural resources and ecosystem. There are 3 pillars of sustainable development and sustainability. Social sustainability, which is related to people, environmental sustainability related to this planet, economics, which is related to profit. So the balance of 3 P's, that's people, planet, and profit in harmony, can achieve sustainability to make this planet a better place to live for generations to come. The 3 pillars of sustainability are powerful tools for defining the sustainable development problems. This consists of 3 parameters: economic, social, and environmental pillars. If any one pillar is weak, then the system as a whole is unsustainable. Social sustainability is the ability of a social system such as country, family, or organization to function at defined level of social well-being and harmony indefinitely. Problems like war, endemic poverty, widespread injustice, and a low education rate are symptoms of a system that is socially unsustainable. Environmental sustainability is the ability of the environment to support a defined level of environmental quality and natural resource extraction rates indefinitely. This is the world's biggest challenge. Economic sustainability refers to practices that support long-term economic growth without adversely impacting social, environmental, and cultural aspects of the community. Well, this is a snapshot of the 17 the global goals for sustainable development that was signed and agreed upon by more than 100 countries, including India at UN United Nations, to achieve by 2030. And India is moving towards this direction, implementing new policies and decisions towards protecting environment, water conservation, vehicular pollution norms, alternate use of renewable energies like solar and wind energy for power generation, alternate fuels for transportation to reduce dependency on fossil fuels. There are some of the challenges for sustainable development the whole world is facing, including India. There's a population growth. These are the challenges we are facing and need to address for sustainable development. There are many environmental issues we are facing today: air pollution, water pollution, garbage, industry waste. Even though we have made noticeable progress in addressing these issues, but has a long way to go to reach environmental quality similar to those enjoyed in developed countries in the world. Pollution still remains a major challenge in India and one of the primary causes of disease, health issues, and long-term livelihood impact for India. Population, India ranks second after China in its total population, leading to problems that include food deficits, sanitation, deterioration, and pollution. Air pollution is the biggest causes are vehicular pollution, thermal power plants, construction dust, waste burning, and fumes. Depletion of natural resources, water scarcity, global warming, ozone depletion, deforestation, poor water supply and sanitation, loss of biodiversity, and increasing air pollution are the concerns and challenges we are facing. Now, there are three ways in which chemical engineers is preserving the environment. Almost everything we use daily, one way or other, we use chemicals, in spite of negative image chemicals are associated with. However, there are scientists and chemical engineers who work with chemicals to make our ecosystem more sustainable. Here are the three chemical engineering practices which are transforming environmental conservation. Cleaner water. The ever-increasing population has put a huge strain in our clean water resources. This is why chemical engineers are coming up with innovative ways of creating water so that it is safe to consume and also that water can be reused. Chemical engineers found ways to remove harmful pollutants from all the sources of water, be it in a raw source or contaminated wastewater. They have developed much more cost-effective methods to do this than what methods we used to use before. Chemical engineers have purified water from rivers and lakes so that we can have clean and potable drinking water. They also effectively treated municipal wastewater and sewage to make it safe for reuse. These methods alone have reduced the amount of waste as well as created safe water for consumption without depleting our dwindling water sources. Cleaner burning fuels. More than half of the carbon monoxide and nitrogen oxides in the air are released through vehicular exhaust. This is why chemical engineers have worked on procedures such as hydrotreating. This uses hydrogen gas and catalysis to produce gasoline and diesel fuels. Fuels made with this process have lower levels of sulfur and lead, releasing fewer pollutants and improving air quality. Improved recycling. When we recycle, we are doing two important things. One is that we are reducing waste, and two, And the second is we are eliminating the need for more raw material, most of which comes from nature. Chemical engineers have, for example, developed ways to recycle aluminum with the use of chemicals, which was a very challenging process as compared to recycling stainless steel. They have done such a good job with the process that now 2/3 of aluminum cans and almost 90% of aluminum in cars is recycled in United States. To produce 1 ton of aluminum for cans, 5 tons of bauxite is needed, which is now saved because of recycling. Chemical engineers also work on effective ways to recycle paper, plastics, and more. Chemical engineering sustainable development. Improving chemical processes. For sustainable development, chemical engineers are focusing on alternate energy, renewable sources like solar, wind energy, alternate feedstocks like biodiesel for energy, bioenergy, and chemicals, biorefineries, and biomass to liquids. Alternate raw materials, green processes with minimal footprint and minimal environmental impact. Process intensification that minimizes energy losses. Recycling, providing quality water, food, and medicines. Energy. Energy is very important for sustainable development and to achieve sustainability. Chemical engineers are well suited to meet the challenges associated with all types of energy production. They have long contributed to the development of such traditional non-renewable fossil fuel sources as coal, petroleum, and natural gas, and now their efforts have been concentrated on renewable fuels derived from biomass feedstocks, turning renewable energy like solar and wind energy into electricity power, biodiesel, hydrogen fuel cells. A vast array of chemical engineering principles is used to generate electricity and to produce different types of fuel for transportation, industrial, and residential purposes. The products ranges from petrol, diesel to kerosene, lubricating oils, waxes, as well as many intermediate petrochemical products. The chemical engineering community is constantly working to modify and improve the petroleum refining processes to achieve higher conversion rates and greater yields, improve overall energy efficiency, produce cleaner fuels, reduce refinery emissions, and reduce operating costs. Also working on to develop, scale up, and commercialize new processes to produce synthetic liquid fuels. Coming to the water conservation, this is very, very important as far as sustainable development concern in India. Chemical engineering has been playing crucial role in removing harmful, hazardous material from water to make it clean and potable for human consumption. Clean water, which is essential to human health, is also necessary for numerous manufacturing processes in industries. With population and industry growth, the need for cost-effective and economical viable water purification and wastewater treatment technologies has become crucial than ever. Treating contaminated industrial and municipal wastewater and sewage to recycle and make them suitable for reuse. Identify more economical or cost-effective system designs for desalination of water to combat water scarcity. There are few desalination plants in India, in Chennai, converting seawater into potable drinking water. Working on more innovative and advanced technologies to recycle the water for human and industry consumption. Chemical engineers meet environmental challenges as well. Their unique expertise enables them to develop advanced technologies, monitoring devices, modeling techniques, and operating strategies that reduce the volume and toxicity of pollutants allowed to enter the water, air, and soil. Significantly reduce the negative environmental impact of industrial facilities, power plants, and transportation vehicles. Allow greater use of post-consumer and post-industrial waste streams, have helped reduce the environmental impact of gasoline and diesel-powered cars, buses, and trucks. Chemical engineers working with scientists and other engineers have helped devise ways to cost-effectively reduce the amount of pollution produced by petroleum fuel burning engines. Key developments include improved engine with more efficient fuel and air management systems, catalytic devices that destroy pollutants found in exhaust tailpipes, and advanced petroleum refining techniques that produce cleaner burning fuels. Global warming measures. One of the most effective ways to prevent global warming is to start using renewable energy sources such as solar, geothermal, wind, and biomass, and stop using fossil fuels. Use renewable energy resources to supply power to your home. Waste material recycle. Recycling is processing used materials waste into new useful products. This is done to reduce the use of raw materials that would have been used. Recycling also uses less energy and great way of controlling air, water, and land pollution. Pollution prevention and control. Adopting stricter vehicle emission norms. For automotive vehicles, switching over to alternate fuels with low or no emissions like electric CNG powered vehicles. This will also minimize dependency on fossil fuels and also import of crude oil, which around 70% of crude oil India is importing to meet the demand. Advanced process control systems to make process energy efficient, less pollution, less wastage, and less byproducts, and the usage of biodegradable green products. Chemical engineering system developed in the field of biodegradable plastics. Material science is one of the broadest and most active areas in chemical engineering. It involves the discovery, evaluation, and manipulation of useful properties in different substances. Chemical engineering community has been working on biodiesel plastics produced from such renewable raw materials as corn, soybeans, and other agriculture and forest crops. This results in greener plastics that not only help reduce reliance on fossil fuels, but are also more biodegradable. By characterizing and then modifying molecular structures, chemical engineers are able to enhance desirable physical properties and performance attributes and suppress unwanted ones. With each new development, a greater understanding of the complex relationships between specific modification and the changes they bring about is achieved. Chemical engineers are developing advanced materials with superior properties that allow for successful performance under increasingly punishing operating conditions. Initially created to respond to the challenges of space travel, many impressive advances have been made using materials from each of the major materials plastics, ceramics, and metals. High-performance plastics are replacing more traditional materials for use in hostile environments. These advanced plastic possesses such characteristics as exceptional strength, lightweight, temperature resistance in excess of 1600 degrees centigrade, chemical resistance, and dimensional stability. They are also relatively easy to process, can be colored or transparent, and can be molded to create desirable structures. Nanomaterials. Incredibly small, nanoscale materials are produced with particle size measured in terms of nanometers. A nanometer is equal to 1 billionth of a meter. In recent years, chemical engineers have been responsible for engineering systems able to produce and use ultra small particles in a growing number of applications, from sunscreen to biomonitoring sensors that can explore inside a cell. The field of nanotechnology, one of the newer areas of material science, makes use of functional advantages that many materials demonstrate when they are produced in extremely small particle sizes. Prefix nano itself refers to a 1 billionth, and in nanotechnology, the basic unit of measurement is a nanometer, which is 1 billionth of 1 meter. A growing number of nanoscale materials and nanotechnology related manufacturing techniques are already being used to produce advanced composite materials that have such improved properties as electroconductivity, catalytic activity, hardness, scratch resistance, and self-cleaning capabilities. Produce consumer products such as cosmetics and sunscreens that have improved aesthetics appeal and effectiveness. Improve the performance of compact, ultra-sensitive sensors and other analytical devices used for detecting disease, monitoring food quality, and assessing environmental, radiological, biological, and nuclear hazards, and enable such medical advances as nanoscale drug delivery particles that allow for the earlier diagnosis and improved treatment of cancer and other diseases. Chemical engineers include their contributions, the discovery of fertilizers, pesticides, and herbicides that protect and enhance fruit and vegetable growth. Innovations in food processing and packaging that help improve taste, appearance, and nutritional value while increasing safety, convenience, and shelf life. And new sterilization techniques that protect food against spoilage and people against foodborne illnesses. Efforts were focused on two general areas: fertilization to promote growth and increase crop size, and protection from pests and weeds to reduce damaged crops. Food purification during processing is essential to remove such contaminants as salts, metals, bacteria, fungi, and pathogens. Membrane-based separation systems pioneered by chemical engineers have now become the purification methods of choice for many food processors. Most food ingredients and processed foods contain unwanted contaminants such as suspended solids, dissolved salts, metals, bacteria, fungi, and other pathogens. Chemical engineers have invented a variety of processes to remove these substances, thereby improving food quality, safety, and aesthetics. One of the most widely used processes today is membrane-based separation. Chemical engineers have responsible for commercial scale sterilization techniques such as high temperature, high pressure, and vacuum and preservatives. Genetic modification, the cross-breeding of plants over many generations was once required to produce food with more desirable or enhanced traits. Now with the techniques developed by chemical engineers, genetic materials can be quickly and precisely transferred from one organism to another. Among the results are stronger, more nutritional products. Plants that have been modified genetically may be used to produce crops with higher nutritional content, greater resistance to herbicide and pesticide damage, increased resistance to disease. Genetic modification is a technique for changing the characteristics of a plant or organism to produce more desired traits. Chemical engineers continue to work with food scientists and biotechnologists to develop more advanced techniques to transfer genetic materials from one organism to another. Genetic modification of foods is one of the most promising and safest strategies available to increase total global food production, reduce crop losses, and increase nutritional content. In the sustainable development of society, chemical engineers play a major role. Due to requirements to use renewable raw materials and energy resources, to reduce number of amounts of secondary desirable products and the pollutant risk, to realize new renewable materials with high properties. So the role of chemical engineer is to use acquired skills to improve the quality of life, foster employment, advance economic and social development, and protect the planet through sustainable development. Chemical engineers have the ability to contribute towards sustainability not only by coming up with processes to use resources more efficiently or reducing harmful waste, but primarily by making these processes economically favorable and viable. Another way to think about sustainability in relation to chemical engineering is green engineering. Green engineering can be defined as the design, commercialization, and use of processes and products that are feasible and economical while minimizing pollution at the source and risk to human health and the environment. So chemical engineering is a remarkable profession. It can take the smallest of discoveries in laboratories from all fields of science and technology and replicate them on a mass scale consistently and economically. So this is a simple definition of chemical engineering. Chemical engineering is all about converting raw materials into useful products in a safe and cost-effective way. It is a difference between a chemistry and a chemical engineering. Chemistry is an integral part of chemical engineering, and both are interconnected. Chemistry revolves around atoms, molecules, elements, and compounds that get together to cause reactions. Chemical engineering is the branch of engineering that combines the knowledge of chemistry, physics, mathematics, and economics to efficiently use produce, transform, and transport chemicals, materials, and energy, and often called as universal engineers due to extensive knowledge base and abilities. Chemical engineers manage resources, protect the environment, and control health and safety procedures while developing the processes that make the products we use and depend on. So chemical engineer, in a nutshell, chemical engineer is a confluence of, or you can call it the Triveni Sangam of science, maths, and economics. And that's the reason they have been referred as universal engineers. So chemical engineering is a branch of engineering that combines the knowledge of chemistry, physics, mathematics, and economics to efficiently use, produce, transform, and transport chemicals, materials, and energy, and often called as universal engineers due to extensive knowledge base and abilities. The main role of chemical engineers is to design and troubleshoot processes for the production of chemicals, fuels, foods, pharmaceuticals, and biologicals to minimize productivity and product quality while minimizing costs. Chemical engineers are in great demand because of the large number of industries that depend on the synthesis and processing of chemicals and materials. In addition to traditional careers in the chemical, energy, and oil industries, there are increasing opportunities in biotechnology, pharmaceuticals, electronic device, fabrication, and environment engineering. Chemical engineers work in almost every industry and affect the production of almost every material manufactured on an industrial scale. Some typical tasks include ensuring compliance with health, safety, and environmental regulations, conducting research and improved manufacturing processes, designing and planning equipment layout, incorporating safety procedures for working with dangerous chemicals, monitoring and optimizing the performance of production processes, estimating production costs. There are plenty of variety and exciting career for chemical engineers. Competitive starting salaries, chemical engineers earn more than the average salaries. Opportunities to travel to the world with the new innovative technologies and idea shares and all. Potential to help create sustainable planet. If you really see that the chemical engineer has a broader scope, like broader scope as far as job is concerned, job prospect is concerned, like they can be a plant, they can work in a plant design, project commissioning, process optimization, plant operation, environment and waste treatment, safety, sales and marketing also, especially for value added or specialized products, distribution for handling hazardous flammable chemicals, and of course education in engineering institutes. These are the tools chemical engineers use and can be learned while engineering. 4 years of engineering like maths, chemistry, mass, energy and momentum balances, thermodynamics and kinematics, process control and optimization, transport phenomena, unit operations, chemical reaction engineering, modeling and computation. Now these tools or syllabus, they can be learned during the engineering and they can apply once they embark on a professional career. Okay, now these are the future demand for chemical engineers like space fuel processor. Now space tourism will initially involve just 2 to 3 hours suborbital flights, but this will gradually develop into longer voyages with flights lasting several days or weeks to allow visits to distant planets or space station. So chemical engineers are currently working to find new source of fuels, biorefineries, wind farms, hydrogen cells, and fusion technology. This could be applied to fuel space travel. Genetic farmers, yes, farmers of the future will not only raise livestock and agricultural crops, they will also grow plants that have been genetically engineered to grow therapeutic proteins, pharmaceuticals, and chemicals. Hence, they are genetic farmers. Chemical engineers are already working on producing vaccine-carrying plants. A recent example which I would like to share here is that come to the light in Ebola epidemic. tobacco plants have been engineered to grow the antibodies for the Ebola serum. I think this will be a key area in the future where chemical engineers can have a huge role driving these processes further to achieve better results. Nano manufacturers, nanotechnology. With advances in nanotechnology already offering a huge range of nanoscale processes, a new group of nanochemical engineers will be required to manufacture these systems. Nanotechnology essentially just the manipulation of very small, as I already shared, matters measuring 1 to 100 nanometers. Some experts think that the next decade will see an increase in manufacturing that are highly skilled and knowledge intensive, and this will lead by nanotechnology advances. This explosion of technological advances in nanotechnology will create opportunities for chemical engineers to lead the way. Green process technology. The focus of all chemical engineers is to work sustainably. Industry experts and manufacturers worldwide are increasingly embracing green technology for sustainable development, water management, and energy efficiency. Developing environmentally friendly chemical processes and products, select processes that minimize pollution, use less hazardous materials, and develop alternative reactions. So this is all about chemical engineering and how chemical engineering contributing to the sustainable development and achieve sustainability in generation to come. Thank you very much for listening, and I wish all the students a very bright future and a great career ahead. Thank you very much.
Thank you for the presentation, sir. We have a few questions from the audience.
Hi, good afternoon. Very good afternoon to all. Yeah.
Okay, so we have a question from
Am I visible?
Yes, sir.
Okay, yeah. Yeah, go on.
We have a question from Shashank Sharma. What is the essential sources of sustainable development in environment?
Sorry? Hello?
Yeah. What is the essential sources of sustainable development in environment?
See, first, I think we need to understand, our dependency on fossil fuels. Okay, now we need to switch over to, more renewable energies like, wind energies and solar energies, which a lot of work has been already doing on, even in India also. So non-renewable energies, renewable energies like wind, solar would be the future, and it will reduce our dependency on fossil fuel, which is depleting faster.
Okay. We have a question from Neha Sundar. How can artificial intelligence be incorporated with chemical processes to attain sustainability?
Okay, this is very futuristic question she has asked. Okay, now see, any computer or IT, even in what you call the humanoid or robotics, you need to have a basic understanding of engineering or chemical engineering. So I could see a huge potential, even if you can see application of robotics in improving the process dynamic and advanced stages of process engineering. But for that also you have to have chemical engineering to to direct that robotics in future. So IT definitely is going to play artificial intelligence definitely is going to play a role again in cooperation with the chemical engineers in future.
Okay. The next question is, what are the steps chemical engineers would take toward handling biodiversity and sustainability? Like I heard that Netherlands have an excellent biodiversity in city, whereas we in India consider biodiversity as a possibility in rural areas.
See, if you really ask me, we have still way ahead. We are still lagging as far as developed countries are concerned. But a lot of change, a lot of steps has already been taken by the government. Government also like plantation of trees, again to recycling of water to make it potable drinking water because it is also depleting faster and scarcity of water. So these are the, you can say forestation, planting of more trees definitely will survive in a longer way, you can say.
Yes, sir. Can you please elaborate a little more on aluminum recycle?
Okay. Okay. Now that research, it's still, you can say, new, but USA has been using, in recycling of aluminum, especially cans and all, and there and this what you call automotive sectors or automotive parts are being used from the recycled aluminum. This is still a novel concept, you can say, in India also, but a lot of research has been taken place. A lot of companies like BSF, DuPont and Dow's are working on that to bring in that technology in India as well. So in future, you will find, what you call a lesser kind of weightage of cars, engines in future, in automotive sector, especially.
Okay. This question is from Chinmay Joshi. How does a pandemic like the one we have when we are facing right now affect the sustainable development?
Hello, yeah, sorry.
I'll repeat. How does
Yeah.
a pandemic like the one we are facing right now affect the sustainable development?
See, chemical engineering has already been successful in Ebola vaccine, and I'm pretty confident that a lot of research parallelly must be going on, even in serum technology in Pune. A lot of research, chemical engineers, along with the scientists and chemical engineer and chemists, working together to form this vaccine. So I'm pretty confident, definitely the vaccine, chemical, because see, innovation is a one part, and to make it commercially viable and economically sustainable is other part, and that's where the chemical engineer plays a significant or pivotal role.
Okay. We have a question from Jitendra Malasare. How will decentralization of energy resources affect our dependency on non-renewable energy resources?
Yeah, because see now, if you really like, for example, in metros, I could see a lot of electric buses are plying, even in Delhi metros also. So slowly, we are switching over from fossil fuels to our dependency on fossil fuels to alternate fuels like electric car, battery operated cars, on automotives. It will take time. It's a again what you call a time consuming process, and it will take time. But slowly, we already started moving into that direction.
Yes, sir. Okay. This question is from Devi Priya Mudir. What do you think is the biggest challenge in adopting sustainable solutions in Indian scenario?
Okay. Now, as far as India is concerned, number one is water, and number two is pollution, industry, and vehicular pollution also. But yes, government is doing a lot of what you call work is going on, like stricter pollution norms, emission norms for automotive vehicles. Then a lot of incentives is going to be kind of battery operated electric cars also. But these are the two challenges, main challenges, because population is also growing, and the natural resources are fastly depleting also.
Okay. The next question is solar energy conventional or non-conventional? And is it a sustainable solution for energy production?
Okay, now solar energy, if you really see, it is not been successful in India the way we anticipated. Okay, because it's again a capital intensive also, and the government should kind of give incentives. Then only it is going to be sustainable. Otherwise, it's very difficult. So we need to kind of follow what other countries or developed countries are, already making this as successful.
Okay. The next question is, what is your advice to young chemical engineers?
You have huge potential and opportunities in future, and future sustainability is in your hand. So if you really say, and chemical engineer can work almost in any industry.
Okay.
So there is huge scope of that. And
Yeah.
you will be an integral part of sustainability in future, not only in India, even on this planet.
Yes, sir. The next question is biodegradable plastic economical?
We have made it economical. I must share one example, live example, since I was working for BASF, and they have come up with a biodegradable plastic. It is already commercialized, and it can be used in agriculture also. You might have heard of mulching. It can be used as. It's a Israel technology, and it's biodegradable within two to 3 hours. That gets and it's harmless. Even cow also eat that biodegradable. It is not going to happen or adverse impact on this thing, animal.
Okay, sir. This question is from Rachakonda Shrikant. Are genetically modified organisms acceptable?
Yes, even in India also.
Okay.
It is being used in agriculture also. Brinjals, potatoes, and other fruits also. It's being used.
Yes, sir. Okay, the next question is, why use of renewable energy is limited?
See, it is not limited, but it is not going the way. The pace is, for example, see, India has ample of free space. If you like, for example, if you go to the Coimbatore, you will find kilometers or miles of wind energies over there, wind turbines, even in some part of Maharashtra also. But because of it is capital intensive, a lot of investment, you have to pump in a lot of money in that to make it viable, commercial. So a lot of research has been already taken going on in that to how to make it commercially viable or sustainable. So because we have space is not a constraint at all, and this requires a lot of space also.
Okay. The next question is from the audience. How is the energy? Are the energy resources tested digitally? And if yes, then how?
Tested digitally?
Yeah.
I have no idea about this.
Okay. The next question is, how do process intensification minimize energy requirement?
Okay, now a lot of process advancement, for example, in refineries also, or for example, grid process. So you have to, so you need a very less raw materials, and you have to produce more kind of, and catalyst plays a pivotal role in that, as Dr. Shrikant already covered in his presentation. So,
Yes,
so
sir.
less raw material and more, and to make it energy efficient. So less energy, less pollution, less byproduct, and less wastage. So that's the key.
Okay, sir. That will be all. Thank you so much for
Thank you very much.
clearing
And
out our doubts.
yeah, thank you very much. And once again, all the very best to all students for a bright future. Thank you very much.
Thank you, Mr. Miliend, for your motivational speech and answering all the questions of the curious participants. It was very interesting to hear about your experience. Mr. Miliend has touched upon all the corners of sustainable development. He emphasized the role of chemical engineering in sustainable development and how we must balance the three pillars to achieve the sustainable development. So the ultimate goal is an improved lifestyle, but at the same time, preserving the natural resources through recycle, reuse, and reduce. May I now request our co-convener, Dr. Elizabeth Joseph, to give the concluding remarks for our webinar. Thank you, ma'am.
Hello, everyone. Now we have come to the end of this webinar. I'm sorry for the delay. My system got hung. During this webinar, I would like to thank all our speakers who have made the sustainability topics very clear to us. Their presentations were extremely specific, concise, and help us to understand the topic. All the speakers, thank you, Professor Neeta Mehta, for sharing the screen. This is the whole thing of internet, quite unpredictable. Can we just click once more? Thank you. Yes, yes. Here are the speakers who helped us to visit the entire spectrum of sustainability. Together, they explored the potential of sustainable practices in chemical engineering. The chemical engineering practices towards sustainable environment was made so clear to all of us. Thank you to all of you. On the first day, we visited the advanced separation processes like reactive adsorption for carbon dioxide mitigation. Mr. Tushar Javeri elucidated industrial water treatment. He helped us to understand the classification. What are the treatment methods? And how to make practices to have a generation having an environment that will be livable. Today, we had Dr. Shrikant Vemula, who explained to us the synthesis of catalyst, the application of catalyst and catalysis for sustainability. The question answer sessions thoroughly cleared the doubts of the participants. Thank you very much, sir. Mr. Miliend Sawai entirely covered up the spectrum of sustainable development and chemical engineering. Thank you very much, sir. Answering so many questions which have popped up from all of us. Thank you so much. The versatility of chemical engineering would not have been visited this clearly if it was not for all of you. Thank you. Ma'am, can you just click the next slide, please? Yes, please go on. Thank you, Principal Sir. I would like to thank our Principal, Dr. G.T. Thampi, who has been a constant, continuous support and guidance for us. Thank you, sir. Ma'am, you can continue. Yes, thank you. This is the team that walked us through the broadcast with all the initial glitch we faced. Thank you, Professor Monica Tolani. Hats off to you and your team who just walked us through this. Thank you so much, each one of you. This is a special characteristic of Thadomal Shahani Engineering College. We just work together. It is a family to be in.
Thank you, ma'am.
Cross-disciplinary. We just lend support. We don't look what time of the day it is. That is Thadomal Shahani Engineering College. Thank you, ma'am.
Thank you, ma'am.
And thank you each one of us, Harsh Balani, Pallavi, Neet, and there were so many others. Ma'am, the next slide. These are our student volunteers, and these are from chemical. They worked day and night. TSEC has a thriving learning ecosystem where students are encouraged to pursue their talents, their research interest. We allow them to develop by having such a close-knit relationship amongst the teachers and the students. Each student is an asset to the society. Each student is the future of a sustainable tomorrow. And we just love working together. It's such a beauty to see the talent of each one blossom as we all put our hands together and see things unveil. This webinar is a demonstration of cooperation, collaboration, which so often happens at Thadomal Shahani Engineering College, Mumbai. Not all of these are chemical engineers. If you would have seen, the poster was again not made by a chemical engineering student. That's exactly what we say. This is the place to be. It looks like, is it a vote of thanks or I'm propagating the family from where I come? It is indeed a beautiful place to be. I am thankful to our management, thankful for the student community, thankful to my co-faculty. Their pictures are not in. We all work together towards publicity for every small thing that is on the way. This is Narayan Madathil. He was like the backbone among the students. Just a phone call and he is on the run, gathering people. His patience and diligence has paid off. Thank you, Narayan. Continue, ma'am. Please continue. Thank you, Professor Neeta Mehta, for your collaboration, support. We look towards many more of these opportunities to groom the future world. The most important, ma'am, you can stop sharing the screen. Thank you. The most important part of the webinar are the participants. We had participants from India and abroad. We're so happy to see so many of them register. Even yesterday, we had participants even from abroad. The whole dividing wall has fallen for the good. We together globally, we will work towards sustainability. We would like to say that we would edit the video of the first day. We are sorry for the difficulty that you faced due to our small difficulty in the broadcast. So we will make it available to you soon. With this, thank you so much. We end the webinar. Stay healthy and safe. Thank you, everyone.